When most of us think of garnets, we think of those singular, well-formed crystals and even the finished gemstones for which the mineral is most known. But I have not seen too much attention given to garnet as being a significant rock-forming mineral, especially in many metamorphic rocks. Join me as we look at a wide spectrum of rock samples collected in the Cache la Poudre River in northern Colorado, which flows through a canyon of spectacular geology and petrology, resulting from the deep basement rocks being uplifted during the Laramide Orogeny and its associated metamorphic processes. Here we are seeing perhaps one of the more attractive occurrences in our local geology, which is Garnetiferous mica schist. And ours is with biotite mica, which creates a uniquely beautiful hand specimen because of the rich golden hue of the mica contrasting with the color of the garnets. I have not yet seen gem quality garnets come out of this material, but they are likely around someplace. The rock is believed to have originally been sedimentary rocks such as shales, mudstones, and clays, which were subjected to medium to high-grade metamorphism through extreme heat and pressure, which recrystallizes the original constituent minerals, causing the formation of flat, platy mica crystals, usually muscovite or biotite, and harder, rounder garnets, which are known as porphyroblasts. And this combination often causes very unique patterns within the rock, such as this example of a similar rock known as augen gneiss. The word augen simply meaning eye-like. Amphibolite is a dark, heavy metamorphic rock consisting of amphibole minerals such as hornblende and actinolite, along with some pyroxenes and plagioclase feldspar. It is believed that these rocks were originally mafic igneous rocks, such as gabbro or basalt. Similar to the mica schist that we saw earlier, these rocks were then subjected to medium to high-grade metamorphism, usually due to either plate tectonics or, and more likely in our case, uplift and mountain building, or the intrusion of plutonic magma bodies. Generally, the rock appears black and quite sparkly due to the many resistant cleavage surfaces of the crystals, especially when the rock is foliated with crystals aligned and all reflecting in a similar direction. Certain directional pressures cause the crystals to align, thus forming an amphibolite gneiss. Here we are seeing both examples of garnetiferous amphibolite and the garnetiferous amphibolite gneiss, with the only difference being the layered appearance of the latter. Some of my research indicated that these garnetiferous amphibolites likely originated from basalts that were at one time part of the ocean floor. Quite a journey these rocks have been through. Of course, due to its attractive appearance, garnetiferous amphibolite, in whatever form, is highly sought after in the granite countertop industry, where I have much of my background, as the slabs are spectacularly colored, as we are seeing here in these examples. Often when I am rock hounding, I imagine what full-size slabs of a given rock would look like if the unfractured original bedrock could ever be located. Most industrially profitable quarries are on flat land where the batholiths have not yet been damaged by tectonic activity or uplift. This next batch of rocks seem to all be related, just with varying percentages of what appears to be epidote, garnet, and some quartz. My research led me to a rock called skarn, which forms when hydrothermal fluids from gradually cooling plutonic magma bodies penetrate and react with the carbonate rocks such as limestones and dolomites. These recrystallize now as silicate minerals such as epidote, pyroxenes, and garnet, along with a host of others. Many metallic ore deposits are associated with skarn formation. The exact minerals and percentages depend upon both the original hydrothermal fluids, i.e. the composition of the magma body they emanated from, as well as the host rock or protolith being altered by the interaction. I'm including these rocks here due to the appearance of garnet, And in the case of the nearly completely red rocks that barely have any green at all, because of their weight, which is noticeably heavier than normal. This huge cobble that I cut and polished may be related to these, since I do see a small amount of what I have been calling epidote along with the garnet and quartz. But it is clearly a granitic rock due to the huge amount of the pink orthoclase feldspar. Those of you who are deeper into the technicalities of rock formation and naming, do you think this granitoid, which just means a granite-like rock that may have a different name due to precise mineral content, could it have originally formed with the garnets, or is this a product of metamorphism, as in the case of the skarns? Also, given the relative abundance of unakite in the area, would this just be considered a garnetiferous unakite? Again, I am hoping for some comments on these questions. Let's return to the mica schist we were seeing at the beginning of the video, but with more feldspar and quartz content. Remember that these schists were at one time sedimentary rocks, but I am curious if the higher abundance of silica implies that the protolith rocks were containing more layers of sandstone among the shales and clays that are said to originate the mica schist. And I also want to point out that, as we saw in the recent magnetite video, sometimes these garnets appear to be in that eye pattern that we saw in that video. But this time it was the garnet crystal that altered the material surrounding it to appear the brighter color. The Bowen's reaction series explains how, as crystallization takes place within a rock, the minerals crystallize in a certain order, and those first to crystallize alter the remaining melt or viscous material to a different composition, which leads to the next minerals to crystallize, and so on. In the case of metamorphism, the protolith does not melt completely, but is viscous enough that atoms can slowly migrate and form new minerals. These garnets, having extracted elements from their surroundings, led to this unique pattern. Here again is a slab sample from the granite countertop industry of very similar material. So, with all of these unique minerals present in the rocks of the Cache la Poudre Canyon, it should be no surprise that the sand in the river is composed of these same minerals. I am preparing a future video on the processes that I have used to separate these different minerals based on grain size, shape, and weight, using both wet and dry methods. Here I am showing you the two heavier sands that I have managed to extract, which are magnetite and garnet. Watch for that video, as I think it will be interesting to many of you. Well, as always, thank you so much for watching. Please remember to like and share wherever you can, and if you have not yet done so, go ahead and subscribe to keep up with the latest content. God bless you guys. I look forward to seeing you on the next one.